Okay, welcome back. Last video, probably of chapter 2 here. We're going to try to finish out the chapter tonight. Let's talk a little bit about something that maybe I didn't mention in the last video. We'll go back and talk about electron configurations very quickly, and then we'll continue on. We'll talk about orbital diagrams. Why was it that I said, you remember the order of filling way back up here, we got to 7p, and I said that was really as far as you needed to go. Because I could keep going. I mean, technically, there's an infinite number of energy levels and sublevels here. Shells and subshells, same thing. Why did I stop at 7p? Well, remember we're writing ground state electron configurations. In other words, we're writing the lowest energy state, which is the way you would expect to find them 99% of the time. And if you look at the periodic table, what is the largest element you see here in the periodic table? What's element 118? See? And so element 118 has 118 electrons. Is there anything bigger than that? Well, no, that's as big as it gets, right? Well, when you do the electron configuration for element 118, you'll find, we're down here in the S block, and we're down here in the 7 row here. So 7s2, 5f14, remember our order of filling thing we did there. Okay, 3, 4, 5, 6d, 10, 7p6. So is there such a thing as a 8s or a 7g or a 7h? Yes, there is such a thing. There is such a thing as a 3000p subshell. But the thing is, it's going to be empty, because you only have 118 cars to park, so to speak. The largest thing you can find in the periodic table has 118 electrons. And you don't need to go to 3000p to put them in there. It's like building a parking lot for Midland College out in Stanton. Can you build a parking lot for Midland College in Stanton? Yeah, you could build a parking lot out there. Who's going to park in Stanton to go to Midland College? Nobody's going to park in Stanton. Why? Because there's always a closer available space. Does the parking lot exist? Yes, but it's just sitting there empty. It's got weeds growing in it. Nobody ever parks there. Is there such a thing as a 7000D energy subshell? Yes, but the large majority of the time it's just unpopulated because there's always a closer available space. Now, if you give that electron energy and you pop it up to a higher energy shell, it's possible it could end up in that 7000D, I guess. But the odds of it being there are just practically 0. So if you can make it up to 7p, that takes care of everything in the periodic table, and that's why that's as far as you need to go. Make sense? Okay. We got 2 things to talk about tonight on this. We need to talk about orbital diagrams, and then we need to talk about your noble gases. I said we'd talk about that on the next one, so I guess here we are. So I guess I have to keep my promises, right? So let's talk about orbital diagrams here very quickly. Orbital diagrams. Orbital diagrams are like electron configurations kind of on steroids. They show information about the energy shell and the subshell, which is what electron configurations do. See, look, here's your electron configuration. Energy shell 2, subshell S. Energy shell 4, subshell S. Energy shell 3, subshell D. That's what electron configurations give you, is information about the shell and the subshell. Electron orbital diagrams tell you information about the shell, the subshell, but also the orbital and the spin. So they give you more information. Okay? When you're drawing orbital diagrams, here are 2 rules you need to be aware of. Let's talk about them first. The first one is 2 electrons in the same orbital have opposite spins. All right? There are... okay, let's go at it this way. Spin is a certain intrinsic quantity that electrons have, and they behave as if they were spinning particles in a magnetic field. Are they spinning particles in a magnetic field? No. Electrons don't spin, but yet they have spin. Okay? It's basically just a property they have, and there is no real physical analogy I can give you. It's just something that you don't normally see up here. But the easiest way to visualize it is as if it were a particle spinning in a magnetic field. You can actually take your right hand, it's called the right hand rule, and you can turn your fingers in the direction of the rotation. This is a physics thing. Okay, and I hope this isn't backwards on the video here, but take your right hand, turn it this way, and curl your fingers in the direction of the rotation. That's a big hand. If you curl your fingers in the direction of the rotation, your thumb will show you where the angular momentum vector is pointing. Okay, this is a physics thing. Also, if you have electricity running through a wire, your fingers will show you where the magnetic field lines are. That's called the right hand rule. Okay, so if you think about, if I've got let's do it out here. My hand's a little smaller. If I've got a globe, there's two ways I could spin it. I could spin it this way, which I know makes no sense to you, but looking from the top counterclockwise. Okay, that's this. All right. The other way I could spin my globe is I could spin it clockwise, and that's really the only two ways I could do it, right? Well, counterclockwise, notice my thumb is pointing up. That's what we call spin up, or the number is plus 1/2. 1/2 because it's a fermion, plus because this. Okay? Don't worry about the fermion thing. It's fine. All right? If I spin it clockwise, my fingers are rotating this way. Where's my thumb pointing? Well, it's pointing down. So we call that spin down. The electron has a value of spin of minus 1/2. And those are the only two allowed values you can have for spin, is plus 1/2 and minus 1/2. It's really, most of the time, kind of like heads and tails on a coin. It doesn't matter. Half the time you flip it, it's head, half the time it's tails. Okay, so if you're not in a magnetic field, each of those are equally likely. In fact, an electron really doesn't have any spin at all until you observe it. And when you observe it, all of a sudden it collapses into one of those two spins, either plus 1/2 or minus 1/2. When you're in a magnetic field, it does matter. Typically, the spin will align with the magnetic field. That's the lower energy situation. Or against the magnetic field is the higher energy situation. But if there is no magnetic field, it's like heads and tails. It's like flipping a coin, and then the coin is in the air. It's not heads or tails, but when it hits the ground, it never lands on the edge. It's always either heads or tails. That's kind of the way it works. Okay? If you put two electrons in the same orbital, they will always have opposite spins. Okay, this is something called the Pauli exclusion principle, which essentially says no two electrons in an atom can have the same energy state. If the electrons are in the same orbital, then they have the same energy shell, they have the same subshell, and they're in the same orbital. So energy-wise, they're all the same. All right. So when you put two electrons in the same orbital, you have to give them opposite spins, because you can't have the same spin, because then they'd have the same energy state. And that's just a property of fermions. Fermions work that way. Protons are fermions, neutrons are fermions, electrons are fermions. Photons are actually bosons, which have integral spins. And yeah, you can have two with the same state there, but that's way beyond the scope of where we're headed today. Basically what it comes down to is when you put two electrons in the same orbital, they have opposed spins. Physically, the reason behind that is if you have opposed spins, that minimizes the repulsion. Okay, I'd say it gets rid of it, because I mean they're both electrons, right? They both have negative charge. But there's a lower energy situation like this than like that or like that. And physically, I guess that's kind of the reason why. So we'll go with that. Okay? The second thing you need to know about drawing orbital diagrams is when several orbitals of the same subshell are available, the electrons enter singly with parallel spins, and that's something called Hund's rule. And that one is a whole lot easier to show you than to try to explain. So let's do some orbital diagrams real quick here and see if you can do these. I think what we're going to do is we're going to do oxygen, we're going to do sulfur here for the orbital diagrams. And the reason why is because we've already done the electron configurations for those. And so if we do the orbital diagrams, you can see how the orbital diagrams are similar, and you can also see how they're different. So let's look at oxygen. Okay, so oxygen, I've got what, 8 electrons? So where do those 8 electrons go? Well, the first 2 electrons go into that 1s. Remember 1s2? Okay. How many orbitals are there in an s subshell? Well, there's only 1. Remember, it's that spherical shaped one? Okay. Well, here it is right here. There's your 1s orbital. Okay. How many electrons can I put in that orbital? 2. Any orbital holds 2 electrons. Remember, we talked about this? So I'm going to put the first one in spin up. Okay. Does it have to go in spin up? No. It's like heads and tails. It could have gone in spin down. By convention, we normally just put it spin up because it's just what we do. But if you put it in spin down, that would be fine. If you want to be different, I guess you can do it that way. But if you put the first one in spin up, the second one has to go spin down. There's no choice. If you put the first one in spin down, the next one has to be spin up. Opposite spins. That's the Pauli exclusion principle. Okay? What comes after 1s2? Well, 2s2. Here's my little 2s orbital that makes up the s subshell. 2 electrons, 1, 2. Okay, what comes after 2s? Well, 2p. How many orbitals are in a p subshell? Well, remember there are 3 p orbitals. Remember your p sub x, your p sub y, and your p sub z? Okay, well, here they are. P sub x, p sub y, p sub z. Together, they make up the 2p subshell. All right, I have 4 electrons to put into my 2p orbitals. Watch the way I put these in. 1 here. Okay, now electron number 2 has a choice. It could either come in and pair up here, or it can go here into a separate orbital. Well, remember, these are degenerate. In other words, they're the same energy. Okay, so I can either pair up here, spin down, which will minimize the repulsion. But did I say it gets rid of it? No, I said it minimizes it. Or here's another orbital over here, equal distance away from the nucleus, same energy, but I got an elbow ring. So, you know, if there was someone sitting in the classroom and you came into an empty classroom, where are you going to sit? You going to sit right next to them, pull the chair right up there against them? No, you're going to give yourself some room, right? Well, electrons the same way. So the next one goes into this orbital over here because it's empty. It's got room. All right. Hund's rule says when you put that electron in the second orbital, it has to go with parallel spins to the first. That's the low energy situation. So if I put this in spin up, this one goes spin up. Third electron goes into this orbital over here and also spin up, parallel spin. All right? So essentially what it comes down to is you half fill all the orbitals in a subshell here first. Okay, now electron number 4 doesn't have a choice. So we're going to put him in this one right here. I could have put him here or here, by the way, because they are equally likely to be populated. But by convention, we normally write left to right, so that's probably why we do it that way. But if I put it in this one, it's got to go spin down because 2 electrons in the same orbital have to have opposed spins. Okay? All right. Do you see how that's similar to electron configurations? 1s2, 2s2, 2p4. You're just showing information about the orbitals and the spin. A little bit more information. That's all it is. Try another one. Okay, let's take a look at the sulfur here. 16 electrons. 1s2, 2s2. Okay, here's my 3p orbitals and my 2p. And there's my 6 electrons. 6 electrons go into a p subshell. Okay, watch the way I fill these up. If you get in the habit of writing it this way, you're following Hund's rule, but you're not even having to think about it. If you can do something and not have to think about it and do it correctly, it's hard to make mistakes that way, right? You can think about something else. So watch how I fill these. 1, 2, 3, 4, 5, 6. You see what I did there? I half filled them first. 1, 2, 3, and then I came back in and paired them up. if you get in the habit of just filling up a subshell that way, you're following Hund's rule, and you're not even thinking about it. You don't have to think about Hund's rule. Okay? What comes after 2p6? Well, 3s2. So here's my little 3s orbital. There's my 2 electrons. And then 3p4. Here's my piece of x. There's my piece of y. There's my piece of z. 1, 2, 3, 4. And there you go. That's the orbital diagram. How do you check your work? Count your little arrows. If it adds up to 16, I guess you did it right. So 2, 4, 6, 8, 10, 12, 13, 14, 15, 16 arrows, 16 electrons. Each one of those arrows is an electron. There's your orbital diagram. Okay? Okay, let's do one a little bigger. Let's talk about krypton. Where do I find krypton in the periodic table? Oh, it's a noble gas. Wow, interesting. What do we know about the noble gases? They don't react with anything. Why don't they react with anything? Because they're already very low in energy, very stable. Do you remember we talked about how 2, 10, 18, 36, 54, 86 were the magic numbers? Are they really magic? Let's draw the orbital diagram for krypton and see. So here we go. 1s2, 2s2, 2p6, 1, 2, 3, and then down, 1, 2, 3, 3s2, there's my 3p, there's my 3 orbitals, 1, 2, 3, 4, 5, 6. We're using the order of filling that we talked about in that other video, so go back and look at that if you don't remember that. Okay, 4s2, there you go. Okay, 3d10. Okay, look. 1, 2, 3, 4, 5 d orbitals in a d subshell. Remember? One of them looked like the little p with the ring of electron density around it, and 4 of them were those 4-lobe cloverleaf shapes. There's your 10 electrons in a d subshell. See, and there they are. Each one of these lines is one of those orbitals. Okay? 1, 2, 3, 4, 5. Now pair them up. 6, 7, 8, 9, 10. Just get in the habit of filling it up that way. You're following Hund's rule, not even having to think about it. Okay? And then you end up on 4p6. Up, 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 down, down, down. And there you go. That's krypton. Count them up. I'll bet you get 36 electrons. Okay. What can you tell me about this outer S and this outer P in that krypton atom? It's full. If I can somehow fill up the outer S and the outer P in an atom, that's a good thing. That actually makes it really stable. And that's what your noble gases all have in common. Their outer S's and P's are full. And so these numbers over here are actually not magic at all. They're the numbers it takes to fill out the outer S and P subshell in an atom. Helium is the exception to the rule. It's 1s2. But once you do 1s2, you filled up the first energy level. See? I mean, there's no 1p. All right? But when you get to 2, yeah, it's your 2s and your 2p, and your 3s and your 3p, and your 4s. Yeah, you got the 3d in there, but your 4p. So that's what's special about 2, 10, 18, 36, 54, and 86. It's actually not magic. It's science. It's the number of electrons that you need to fill out the outer S and P. That's what makes those atoms really, really stable. See, I do follow through on my promises. It just takes me a while sometimes. All right? How many electrons can I fit in an S subshell? 2. How many electrons can I fit in a P subshell? 6. What's 2 plus 6? 8. 8 electrons. 8 electrons in the outer subshells. 8. File that away for future reference. That number might become important someday. Okay? Okay. Well, if I can abbreviate electron configurations, can I abbreviate orbital diagrams? Sure. And I do it exactly the same way that I did for electron configurations. All right? Go through your periodic table. So, for example, if I'm doing krypton here, find the last noble gas you get to, going through the periodic table until you get to krypton, and that would be argon. So we're going to put argon in brackets. You can't put krypton in a bracket and then just write it down. That's cheating. Can't do that. Got to go to the last noble gas. All right. So we go to argon. That takes care of the first 18. Okay. What comes after argon here? We're in the fourth row. We're in the S block, so 4s2. Remember, this is fourth row, I know, but the D's are offset, so this is 3d10, and then back to the P block where you're back to row 4. 4p, 1, 2, 3, 4, 5, 6. Remember? And so, argon, here's my 4s2, one orbital and an S. Any S also has one orbital. Here's my 3d10. There's my 5d orbitals in a D subshell. And then 4p6. And there's my 3p orbitals in a P subshell. P sub x, P sub y, P sub z. And there's my 6 electrons. Notice that everything is paired in the orbitals. 2 electrons in the same orbital have to have opposed spins. Count them up. Bet you get 36 arrows. 36 electrons. And that's how you do an orbital diagram. Spin and the orbital really only comes into play in a magnetic field. If you don't have any magnetic field, an electron in this orbital is the same energy as that orbital, and spin up, spin down equally. It doesn't really matter as far as the energy goes. So that's why electron configurations work just fine most of the time. If you're in a magnetic field, now it kind of, if you have orbitals lined up with the magnetic field or against it or sideways, now it becomes an issue. And so, yeah, you need to worry about this stuff. Okay? If you have unpaired spins, arrows that aren't paired in a substance, it's called paramagnetic. I'm going to toss that in there for you. And what that means is it has certain magnetic properties. This has to do with magnetism. A lot of unpaired spins usually means pretty magnetic. If you have no unpaired spins, then that substance is called diamagnetic. All right, and that has different magnetic properties. We'll just go that way. So, for example, krypton is diamagnetic because, see, there's no unpaired spins there. But oxygen is paramagnetic because you have 2 unpaired spins there, see, and 2 here in sulfur, so it's also paramagnetic. Calcium, if you drew the orbital diagram, it's going to be basically argon 4s2. And if you draw that, you'll see there's no unpaired spin. So calcium is diamagnetic. Silver is actually paramagnetic because you've got unpaired spins in it. By the way, just when we were talking about spin, this is just a historical note for you here. Remember we said silver was really 5s1 4d10? If you did the orbital diagram for silver, what you'll see, if you do it this way, is everything's paired up except for that one little tiny electron in that 5s out there. And that's actually how they discovered spin back in the 1920s. They ran it through a magnetic field, and the silver was just a little wonky there, and it's like, whoa, what's going on there? And it turned out to be that electron with that unpaired spin that was actually causing it. And so that's how they actually discovered spin, was with silver. That's this right here. Okay. Not on the test, but I thought it was kind of interesting. All right. Can you do orbital diagrams? Hopefully. All right, you're on the home stretch. We've got one last thing to talk about. You're almost there. Look. We're down to 1 page. All right. So let's talk about trends in the periodic table. There are certain trends in the periodic table. We've talked about this that you can see before. And remember, the periodic table is arranged according to chemical reactivity. Is the periodic table arranged according to electronic structure, by the way? No. All right. Case in point, here's helium over here. If it was arranged according to electronic structure, where would helium be? It would be over here in the S block right here, right? See, 3s2, 2s2, 1s2. How come it's over here and not over here? Well, because helium reacts like these elements over here, which is to say not at all, and not like an alkali metal over here. And that's why helium is sitting over here. So your periodic table is arranged according to chemical reactivity, not electronic structure. It just so happens that there's such a strong correlation between electronic structure and chemical reactivity, you can derive the electronic structure by looking at the periodic table. But technically, it's actually arranged according to chemical reactivity. Well, there's other trends in the periodic table that you can look at. And so let's look at a couple of those, and we'll call it good for Chapter 2. How about that? So let's look at atomic size, first of all. How big is an atom? Okay. Well, here's the trend. Atoms get smaller going across the periodic table from left to right, and larger going down. All right. So if you look at a periodic table, atoms actually get smaller going across, larger going down. You mean a potassium atom with 19 electrons is larger than a bromine atom with 35? Yes, it is. In fact, it's about twice as big. Okay, why? Well, basically, they get smaller going to left to right because the electrons in the same orbitals are pulled in by a greater, something called effective nuclear charge, going from left to right, and so therefore they get smaller. I can show you. You're probably not going to understand it. You're definitely not going to remember it. So I'm not going to try. All right. So basically what I want you to do at this point is just remember this. Atoms get smaller going across the periodic table from left to right. Doesn't make sense, but that is the way it works. Okay. Just remember it. I think you're better off. All right. Now atoms do get larger going from top to bottom, and that actually makes a lot of sense. Because as I'm going down, see, I'm in higher energy levels. See, this is my, this would be a 2p1, 3p1, 4p1, 5p1, 6p1, 7p1. And so I'm just going out further and further and further. And so, yeah, I mean, you would expect the atoms to get bigger as you go down the periodic table. That makes sense. Going across getting smaller, not so much. But that is the way it works. So basically, your tiny atoms in the periodic table, besides hydrogen, are sitting over here, your oxygens and fluorines and chlorines of the world. Your largest atoms in the periodic table are over here at the lower left, very far down and very far left. Your cesiums and bariums and franciums of the world. Those are your larger atoms. Okay? All right. Trend number 2, ionization energy. Okay, ionization energy is the energy it takes to pull off an electron. Okay, so if I had an atom and I wanted to just kind of pluck one of those electrons off, how much energy would it take to do that? Ionization energy is the electron that gets pulled off is usually the outer electron because, the outer electron is the one that's least hotly held. It's the one that's furthest from the nucleus. Plus the fact, if I want to pull off an inner electron, I got to dig in there and find him. He's way down there inside, and he's really close to the nucleus, so that's going to be hard. If you're going to pull one off, why not pull one out here on the outside that's very far away from the nucleus, right? So it's how tightly are those outer electrons held is really what makes ionization energy. All right? Your trend is ionization energy increases going across the periodic table. It's harder to pull an electron off. See, this is basically your equation here. I've got sodium. I'm going to a sodium plus 1 electron. I kicked an electron off of that sodium. The ionization energy, this is the first ionization energy for sodium. It's 496 kilojoules per mole. So in other words, if I wanted to take 6.022 times 10 to the 23rd little sodium atoms, we'll talk about it, and pull an electron off each one of them, I've got to add 496 kilojoules of energy to do it. Okay? Ionization energy increases going across the periodic table, and it decreases going down. It's easier to pull off electrons as you go down. So what that means is these atoms over here have very low ionization energies. It's easy to pull them off. These atoms over here, it's very hard. Okay? There's a couple of reasons why. Yeah, okay, we'll go there. We won't talk about second and third. That's close enough. Okay? One of the reasons why is size, which we're going to talk about here in a second. The other reason why is there's nothing to be gained over here. See, look, if I lose an electron over here with these atoms right here, well, that gives me a nice double gas structure, so that's a good thing. All right, and so, yeah, it'll give up that electron really easy. If I lose an electron over here, well, that gets me even further away from these noble gases, and so that's a bad thing. So these really don't want to lose electrons. It's hard to pull them off. These give them up almost just too easy, and so therefore they have low ionization energies. Okay? Now, how would I do something like this on a test? Well, rank the following elements in order of, let's say, increasing size. All right, so if I say increasing size, that means what? From the smallest one up to the largest one, right? So you got to read the question first. All right, so I've got cesium, sulfur, oxygen, nickel, and sodium. Okay, well, I know that atoms get smaller going across and larger going down. So my smallest one would be oxygen, see, because it's very far over here to the right and it's very far up. Okay, so what's next? Well, here's sulfur. It's one down, but it's still very far to the right, and so sulfur would probably be next. Okay, and then I've got what? Nickel, and I've got sodium. And this one's a little tougher. This one's one down, but it's quite a bit further over to the right. So I would probably go with nickel here for the next largest. Here's sodium. It's really far up, but it's also very far over here to the left. So it's probably the next largest. This one or this one, you could probably make a case on those, but you know, that's kind of what it would be. And then cesium's the largest one because look, it's very far down and it's also very far over here to the left. All right, and that's how that works. All right. If you're asked a question like that on a test, I'll make it easy for you. You know, you won't have to make any judgment calls. I won't ask you something like sulfur, 10, or aluminum. Well, aluminum, that'd probably be pretty easy. Or nickel. Something where it's a judgment call, you're like, I don't know, it could be this or it could be that. I'm not going to ask you that. If you know the trend, you're going to be able to get this on the test. Okay? All right. Rank the following elements in order of decreasing ionization energy. Okay, so decreasing ionization energy means the highest ionization energy first, down to the lowest. Okay, so the one that's the hardest to pull off. Well, my trend here is ionization energy increases going across and decreases going down. So increases going across and decreases going down. So the highest one would be over here with oxygen, see? Because it's very far over here to the right and it's very far up. Okay. Sulfur is very far over here to the right and kind of up, but not as up as oxygen, so it's probably next. Then I got nickel over here, which is kind of down, but very far to the right, so it's probably next. Then I got sodium over here, which has a pretty low ionization energy because it's kind of up, but it's way over here to the left. You know, there's a driving force behind it giving up bits, and we'll talk about that in the next chapter. And then you got cesium down here, which is very far down and also very far to the left, so that's probably the one with the lowest ionization energy. All right. Notice when we did that, the order is exactly the same, isn't it? Why is the order exactly the same? Well, because there's a correlation between the size of the atom and its ionization energy. If I have a very small atom, the outer electrons are very close to the nucleus. If they're very close to the nucleus, they're attracted very strongly, and so it's going to be harder to pull those electrons off. So therefore, you're going to have a high ionization energy with a very small atom. If I have a very large atom, the outer electrons are way out there just kind of lazily floating around, and so it's really easy to pluck those off. They're going to have low ionization energies. So there's kind of an inverse relationship between the two. Small size, high ionization energy. Large size, low ionization energy. And this is increasing size and decreasing, so that's exactly why these are exactly in the same order. Make sense? Okay, if you can do that, we're going to call that good. And again, if I give you two and say which one has the higher ionization energy, it'll be something that you can look at the periodic table and you will know. I'm not going to give you things that could go 50-50. If you know the trend, you'll get it. And that's kind of the way it works. Okay? All right. Well, guess what? That is Chapter 2. And so you're actually ready for a test. So everything on your first test will be from Chapter 1 and what we've talked about so far in Chapter 2. The next video will start Chapter 3. And in Chapter 3 will not be on your first test. It'll be on your second test, which will be Chapters 3 and 4. And as soon as I get back, we'll talk about when you're going to take that test. Yeah, we'll talk about it. We'll figure it out. But it probably is going to be fairly soon after I get back. So you might want to be watching these videos and start studying. I will throw Chapter 2 homework at you, and I guess it will be due when I get back. Again, email me if you need anything, if you have any questions. I will do my very best to answer them through email. If you can get in touch with me somehow, if you want to fly over and come find me, you can, but you probably don't want to do that. Email might work better. You can try to call me in the office. I won't be here. So yeah, I think email will be the way to go. So you do the best you can. Next thing coming up will be Chapter 3. We'll start on that, and I'll go a little ways into Chapter 3, and then we'll quit, and when I get back, that's where we'll start. Okay? All right. Well, it's not time here, so you can probably see from the window. So I think I'm going to go to bed. So we'll quit there, and I guess we'll see you next time.